how do we proceed now? So the idea is that we need to go to more generalized rates, okay, which have the same physical dimensions of a time derivative, but are really more than the time derivative. And in particular, we want to have some way to get rid of the effect of this rotation, okay, the effect of the rotation rate. Okay, so nullify the effect of q dot. All right. Now, let me just state here that many such rates can be defined. Okay. And the general form of these rates is of these relations then is the following. We have tau. We can compute some general rate of it, and because we have some general rate, I'm going to use that symbol to denote some rate. Okay? That's not a dot, it's some rate, right? It's not just a traditional material time derivative, it's just some sort of rate which has the right physical dimensions of a rate of tau, okay? Of tau. So you can find many such objects which will then allow you to write a relation of the form that. Many rates can be defined to be used in relations of this type. Okay? But when we do that, what is left up to us to model is what that transformation tensor is. Right? So this then becomes an equivalent, it becomes like an equivalent elasticity tensor in omega t. Okay? And a great deal of constitutive modeling for finite deformations, when one wanted to write things out in the current configuration, used to come down to figuring out what, or really to modeling what A had to be. Okay? That was an industry, but it has fortunately been largely bypassed. It's also, I say fortunately because one can very easily get into situations where we get the same sort of problem that I described with hypoelasticity, which is that if A is not properly obtained from the from this notion of hyperelasticity, one can have closed cycles in which one generates work. Okay? I won't get into that because that's an entirely different, that's almost an unending topic and largely leads to wrong results. Okay? But there is a correct and exact way of doing things. And here's what we do. Okay. The idea that we need to follow is to define a rate by pulling back tau to omega naught, okay, which will basically give us S. Okay, we pull it back, apply time derivative, and push forward. Okay? I've written there in words what I'm about to write an equation for. So we start out with tau, current configuration. Pull it back. Now, because of the relation between tau and S, what we have here is S. Okay? Now, this is a material object. It sees nothing about rigid body motions on the current configuration. Okay? Take its time derivative. There is a single time derivative defined here, right? Push it forward. Okay? Why does this work? Let me draw why this works. Omega naught. Okay, we have that, and we're talking of applying rigid motions on that. Okay? Phi plus, right, which is C plus QX. Right? Tau. Pull it back. Okay, pull it back, okay, to S. They're equivalent, right? Under the same state of stress, we have different stress tensors we can talk about. All right? Calculate derivatives here. Okay? These derivatives don't see anything about this motion, right? Anything that we do on S here, right? The step that is enclosed in the bigger parentheses here, right? Above, just above this equation, right? The step that is enclosed in here sees nothing about these rotations, about rotations on the current configuration. This step is not seen back here on the reference configuration. Okay? Push it forward. Okay? We finally have something after pushing it forward. We have something in the final current configuration which sees nothing, right? Which completely misses the effect of the rotation. Okay? Let's see how this actually works out. Okay? All right. Okay? The reason this works is, so let's now consider the following, right? We have tau plus, pull it back, F plus inverse, F plus inverse transpose. Okay, we pulled it back. All right, and then we're going to take time derivatives here. Okay, let's just compute what happens with this step. This is partial with respect to time of, what is F plus inverse? F plus is QF, right? So F plus inverse is F inverse Q inverse, which is Q transpose. Tau plus is Q tau Q transpose. F plus inverse transpose is inverse transpose of QF, which after taking the inverse and the transpose gives us back Q inverse transpose, but Q inverse is Q transpose, therefore Q inverse transpose is Q transpose transpose, which is Q, right? And we have here F inverse transpose. Okay, we're taking time rates of this, but these two terms are gone, right? Isotropic tensor. Okay, so this is indeed exactly the same thing as right, which is basically the time derivative of S. Okay? Okay, so here's what happens. Reference configuration, current configuration, we're going to do rigid motions. What we're saying is you could be even after your rigid motions, right? Just take what you have for tau plus, the transformed components, pull it all the way back to the reference configuration, right? You're back in here. You do have a stress too. We still do have that stress, the second Euler-Kirchhoff stress, which we are working with. Compute how that is changing. Okay? That's what we've done so far. Right? Now push it forward. In pushing it forward, we're pushing it forward with the new F. Okay? Right? Now F plus of the derivative of F plus inverse tau plus F plus inverse transpose. Okay, we take all of this and push it forward with F plus transpose. Okay, and pushing it forward with F plus transpose, what we've done is that we pulled everything back to omega naught, took our simple material time derivative. There is no other time derivative in this configuration. Push it all the way into the post rigid body motion configuration. Okay? In the process, we've completely nullified the effect of those rotations. Okay? This object is called, we're defining this with a symbol that we're going to write as LV of tau. Okay? In this particular case, it is LV of tau plus. Okay, because we're operating on tau plus with it. Okay, this is called the Lie derivative. Sorry. Okay, and we're going to stop here for this segment, but when we come back, we're going to say a few more things and then relate it to a tangent.